Today we'll talk about one of the most ubiquitous problems in AI called classification. Classification is mapping sets of percepts in the world into equivalence classes so that we can take actions in the world in an efficient manner. We could learn these concepts through incremental concept learning. We'll talk about the nature of these equivalence classes and how they can be organized into a hierarchy of concepts. We'll talk about different kinds of concepts, like axiomatic concepts and prototypical concepts. Given a classification hierarchy, we'll talk about multiple processes for doing the classification, including both bottom-up and top-down processes. In the previous lesson, we examined some techniques for learning about concepts from examples. But those were simple concepts that we learned from a few examples. Concepts like arch or concepts like foo, which was our imaginary hypothetical concept. In the real world, concepts can be much more complicated than that. As an example, consider the 8 animals shown here. Each picture shows a very cute animal here. How many of these do you think are birds? Which one are birds? David, what did you think? And tell us also why you chose the answers that you did.
So I said that these 5 were all birds. Each of them have wings, each of them have feathers, and I know that each of them lay eggs. The other 3 are kind of interesting. This is a sugar glider, and it flies, and we often think of flying as a bird behavior, but it doesn't fly the same way birds do, and it doesn't have the other features that birds have. It has fur instead of feathers, and it doesn't actually have wings. And we also know it doesn't lay eggs. A bat is even more interesting. A bat does have wings, but it doesn't have feathers the way birds do, and bats actually give birth to live young. The platypus shown here is an interesting case because it actually lays eggs, it has a bill like a bird does, and it also has flippers the way a duck does. But it's still not a bird because it doesn't have feathers. So I would say that these 5 are all our birds. Some of the things that we often attribute to birds, like flying, that a bluebird, an eagle, and a duck do, penguins and ostriches don't actually do, but they're still birds because they meet our other criteria for birds.
That was a good answer, David. Thank you. Note that David was able to classify these 8 animals into birds. Which one of these animals belonged to the class of birds and which one did not belong to it. Notice also that he used some criteria to decide on that. He has some notion, it seems, of what is a typical bird, what kind of features does a typical bird have. He has some notion of what are the basic conditions that something must satisfy in order to be considered a bird. And if those conditions are not being satisfied, he would reject them and say those are not birds. So here are 4 of the animals that David classified as birds. Let us look at the kind of features that he examined in order to classify whether or not an animal was a bird. He may have used several features, some of which he articulated, others that he may not have articulated. So whether an animal has wings, whether it has feathers, whether it has a beak, and so on and so forth. One could add more features here if one wished to do so. We do classification all the time. AI agents need to do classification all the time also. Why? Why is classification so ubiquitous? To see why classification is so powerful and so ubiquitous, and also to understand what exactly is classification, let us go back to our overall cognitive architecture for an intelligent agent. This is a diagram that we have come across many times. Let us imagine this particular cognitive system is dealing with a set of percepts. These percepts are in the world. So as an example, this cognitive system may see some object, some animal when the cognitive system goes to the zoo. This might be an AI agent or perhaps your friend who goes to the zoo and looks at some animals, and there are a large number of percepts in that environment, has wings, has feathers, talons, beak, and so on. And for the simplicity, let's assume that each of these percepts is binary. It's either true or false. So either the animal has wings or doesn't have wings. Now, depending upon the percepts and the combinations of these percepts, one might take different kind of actions. So if it's a friendly animal, one might go and pet it. If it's a unfriendly or dangerous animal, one might run away from it. So all kind of actions are possible. Imagine that there are some M actions that are possible. So, and we can again imagine that there is a binary choice here. So the total number of combinations of actions is 2 to the power m. So as an example, if I see a dangerous animal in a zoo, then I might both scream and run away. If I see a friendly animal, I may approach the animal and make cooing noise to the animal. So a number of actions and combinations of actions are possible. And if n is the number of percepts, then I have 2 to the power n combinations of percepts possible. So here is the challenge that the cognitive agent faces. The challenge is that the number of percepts and the number of actions, more precisely, the number of combinations of percepts and the number of combinations of actions is very, very large. And we have to map these percepts, combinations of percepts, and these combinations of actions. This is a very complex mapping. So imagine there are only 10 percepts in the immediate environment. So I'm looking at an animal and there are, let's say, 10 percepts that I'm paying attention to. Then 2 to the power 10, the number of combinations of percepts is 1024. I'm doing it 2 to the power 10 here because I'm assuming that each percept has a binary value. If I had 100 percepts, I was not looking at one animal, but I was looking at a scene of animals, then I may have 100 percepts, in which case I have a much larger number of combinations. And if I had something like 300 percepts, which is still not a very large number, the number of combinations is, well, it's a very large number, more than the combinations of atoms in the universe. Now, you and I, and AI agents more generally, are constantly faced with complex environment in which there are a large number of percepts and a large number of actions that are possible. So let's go back to something earlier that we had considered in the class. We defined earlier that one way of talking about intelligent agents is to think in terms of how can an intelligent agent map percepts into actions. Intelligence is in part, in large part perhaps according to this definition, about action selection. The other aspect of this is that if the number of percepts is large and the number of actions is large, then the mapping between them becomes very large and very complicated quickly. But intelligent agents have only finite resources. How is it then that we can select the right action, or at least most of the time select the right action, even when the environment is very complex, and do so in near real time? Here is one way in which an intelligent agent can work in a complex environment in which there are a large number of percepts and actions possible, and yet do so relatively efficiently. Suppose that these 2 to the power n percepts could be mapped into k concepts, where each of these k concepts is an equivalence class for a large number of these combinations. So 2 to the power n may be very, very large, but k is a much smaller number. So these concepts are now equivalence classes of these percepts. So now, instead of indexing my actions on the combinations of percepts, I index my actions on the equivalence classes that I'll call concepts. And this happens all the time. You go to a doctor, for example, and you may go with some signs and symptoms, and the doctor says, well, I have to decide whether I'll give you a blue liquid or a red liquid. Assume that those are the actions possible. And the actions are now indexed not as the signs and symptoms or the combinations of signs and symptoms, which are potentially very large for human beings, but a certain small number of concepts, the number of diseases, which compared to all the combinations of signs and symptoms is much smaller.
Another example of this that would come from computer programming would be that we might have a small number of different ways in which a computer program can go wrong, but a large number of different percepts that tell us what has actually gone wrong. So for example, in my percepts, I might have whether or not I received a null pointer error, whether or not I received a memory allocation error, whether or not I received a index is larger than the size of an array error. All of those are different percepts I might have, but they might map the same underlying concept of something has not yet been initialized. So I'm taking the number of things that I can actually see and mapping them to a smaller number of ways in which the program can actually go wrong. Then instead of having to map each individual percept to some number of actions, I know that if my error is that something has not been initialized, I need to find what hasn't been initialized. And there's a much smaller number of actions involved looking at each individual variable and seeing where the initialization has not taken place.
Now we understand why classification is such an often studied topic in artificial intelligence. Almost every school of artificial intelligence has studied classification extensively. If there were no concepts, we were mapping these 2 to the power n combinations of percepts into these 2 to the power m combinations of actions, then we could think of an intelligent agent as a one large giant table. The rows of that table are all the 2 to the power n combination of percepts, so there will be that many rows, and the columns are 2 to the power m actions. Given a percept, I know exactly what action to take. The table tells me that. But it's going to be a very large table. We don't know how to use it. It will be very costly to use it, and we don't know how to build such a table. What classification is doing is, it is breaking that large table into a large number of small tables. And that's the power of knowledge. When you have knowledge, you can take some complex problem and break into a large number of smaller, simpler problems. So the next question becomes, given a set of animals, or in general a set of objects or elements, and a set of percepts for each of those animals, how can we decide what's a good equivalence class for those animals? Consider, for example, the three animals shown here, eagle, bluebird, and penguin. And let's suppose that we knew that there are 6 percepts that are important for each one of these animals: lays eggs, has wings, has talons, and so on. Well, in order to decide what might be a good equivalence class for these 3 animals, we first have to decide on what might be the right values for each of these percepts for each animal. So I'm going to ask you to use your background knowledge to fill in the values of the percepts for each of these 3 animals. David, do you know about these 3 animals? Were you able to answer this question?
So admittedly, I used Wikipedia a little bit to find out some of these answers, but we know that eagles lay eggs, bluebirds lay eggs, penguins, they all lay eggs, and they all have wings. Eagles and bluebirds have talons, whereas penguins kind of have flippers because they swim, so they don't really have talons. Eagles and bluebirds also fly, whereas penguins don't fly. None of them have fur, and we might say that eagles and penguins are large, whereas bluebirds are not very large. Our definition of large is kind of variable, it's kind of subjective, but if we were to draw a line somewhere, it's reasonable to say that bluebird is definitely on the smaller end of the spectrum.
Good, David. You know more about these animals than I do. Imagine that the 3 animals were given as examples, one after the other. So we are back to incremental concept learning of the previous lesson. One can use the techniques that we learned in the previous lesson to learn some equivalence class, learn some concept definition with these 3 animals. But that's not the point here. The point here is not about the learning of the concept. The point here is much more about the nature of the concepts and how they get organized related to each other. So I just talked about the organization of concepts and the relationship of concepts with each other. We already come across this when we were talking about background knowledge in the previous lesson on incremental concept learning. So we had a brick and a wedge. They were both subclasses of a block. In general, the organization of concepts can be much more complex. So here is a set of concepts that you're probably all familiar with. We have different kinds of animals, vertebrates, invertebrates. Vertebrates themselves can be of different kinds, reptile, birds, mammals, and so on. And here are birds, which can be of different kinds, eagles, bluebirds, and penguins, like we saw in the previous slide. In general, the organization of these concepts can be a little bit more complicated. So this is a conceptual hierarchy that I expect all of you are familiar with. The animals of various kinds, vertebrates and invertebrates, for example. And vertebrates themselves can be of different kinds, reptiles, birds, mammals, and birds can be of different kinds, for example, eagles, bluebirds, and penguins. So these are classes and these are subclasses and superclasses. Now, the advantage of this kind of conceptual organization is that I can start going in a top-down way, establishing and refining each category. So you see an animal and you're trying to decide whether that animal is a bluebird or an eagle or a penguin. And you may start initially by saying, well, is it a vertebrate? Then is it a bird? And if it is a bird, then is it an eagle, a bluebird, or penguin? When you and I do processing of this kind, it might happen so fast that we might not be aware of it. But when we're trying to build an AI agent, we have to make that processing very, very explicit. Even among humans, imagine, for example, what happens when a scientist discovers a new kind of species. Then the scientist will begin from the top and say, well, is it a vertebrate? Where exactly in this tree should I put this species? Is it a bird? Is it closer to eagle? Should I put it closer to a bluebird? And so on. So classification of this kind often has a top-down, establish, refine character to it.
So one of the benefits of this establish and refine approach is it helps us figure out which variables we need to actually key in on and focus on. So for example, we saw earlier that eagles are large, but bluebirds are small. So birds can come in different sizes. So if we're trying to establish whether something's a bird, a reptile, or a mammal, we know that mammals also come in different sizes, like tiny mice or large elephants. So size doesn't really impact our decision whether it's a reptile, bird, or mammal. But once we've established that it's a bird and we're trying to decide between eagle and bluebird, for example, we know that size actually can be something that helps us differentiate between these two. So now we'll pay attention to size as a variable that matters.
So note that there are several things going on here. On one side, there is knowledge of these different classes, but there's also organization of these different classes in a hierarchy of a particular kind. This organization is very powerful. In some ways, if knowledge is power, So is organization. Organization too is power. This organization provides power because this organization tells you what the controller processing should be. Establish one node, refine it. Establish that node, refine it. Let us return to the exercise that we were trying to do earlier, where we had eagle and bluebird and penguin, and we had features and we had values for the eagle and the bluebird and the penguin. Well, given these three sets of values for the eagle, bluebird, and penguin, and given that bird is a superclass of these three classes, what would be the features that you would put in the bird node in that classification hierarchy? What do you think, David?
So what I did is I looked across the rows and tried to see which features all three birds had in common. They all lay eggs, so I'm going to figure that birds lay eggs. They all have wings, so I'm going to figure that birds have wings. And none of them have fur, so I'm going to figure that birds don't have fur. Whether or not they have talons can actually vary, so the eagle and bluebird have talons, but the penguin does not. And whether or not they're large can vary, the eagle and the penguin are large, but the bluebird's not. So those things don't necessarily define what a bird is, but these three things seem to me like they do.
That's a good answer, David, but I should quickly note that this idea that we can decide on the features that should go into a superclass given the features that are shared among the subclasses works only for a certain kind of concept. It doesn't work for all concepts. In particular, it works for concepts that have a formal nature, as we'll see in just a minute. We can think of concepts lying on a spectrum. On one extreme end are extremely formal concepts for which we can define logical conditions that are necessary and sufficient for that concept. We'll examine that in more detail in just a minute. On the other end of the spectrum are less formal concepts for which it's hard to define necessary and sufficient conditions. Now here are 3 points on the spectrum: axiomatic concepts, prototype concepts, exemplar concepts. There can be other types of concepts as well. We're just going to consider these 3 concepts because they are the 3 most common ones, and we'll look at each one of them in turn. In general, humans find it easier to communicate about these axiomatic concepts because they are well defined. There is a set of necessary and sufficient conditions that we all agree with. Examples are mathematical concepts. Humans find it harder to communicate about prototype concepts, but most of the time we do quite well. It's even harder to talk about exemplar concepts like, let's say, beauty or freedom. Similarly, it's easier to teach computers about axiomatic concepts or program axiomatic concepts into computers. It's much harder to program or teach prototype concepts and much harder to teach or program exemplar type concepts. So let us look at each one of them: axiomatic concepts, prototype concepts, and exemplar concepts in more detail. Let's begin with axiomatic concepts. An axiomatic concept is a concept that is defined by a formal set of necessary and sufficient conditions. Geometric objects like a circle are good examples: triangles, squares, rectangles, and so on. So as an example, a circle are all points in a plane that are equidistant from a single point, where a single point is the center of the circle. Now, this is a very formal set of necessary and sufficient conditions. Given any other object, you can see whether or not a particular object is a circle by looking for this particular condition. The notion of axiomatic concepts is the classical view in cognitive systems. Here is an alternative view. This is called prototypical concepts. Prototypical concept is a base concept defined by some typical properties that can sometimes be overridden. So an example is a chair. You and I have a notion of a prototypical chair. Our notion of a prototypical chair may have, for example, that it has a back, it has 4 legs, and so on. So here might be your and my notion of a prototypical chair. It has a back, it has a seat, it has 4 legs, and so on. Now I can represent this notion of prototypical chair in the language of frames. This is something we have come across earlier in the class. A frame has slots and fillers, as you may recall, and we use frames to represent stereotypes. Here we're talking about prototypes, so very closely related. So concept is the content we're going to represent. Frame is the form in which we're going to represent it. So a notion of prototypical chair might be it has 4 legs, the material is a metal, it has a back, it does not have arms, and it's not cushioned. Note that these are the typical properties of a chair. Of course, some chairs need not necessarily satisfy all of these properties. That is why there are no necessary and sufficient conditions here. For example, we may come across a chair which is made of wood. Well, we would still consider it a chair even if it did not strictly satisfy this particular definition. Thus, these properties can be overridden in case of specific instances. but we will still have the basic notion of a prototype of a chair so that we can in fact communicate with each other about what a chair is. Despite the fact that we can override these properties, we do still have a notion of prototypical chair. So the relationship between concepts and frames actually is quite close. Recall that when we were talking about frames, we were also talking about inheritance and default. The notion of default in frames is closely connected to the notion of typical properties in concepts. So chair has this prototypical notion with some of these typical properties, and we can think of this as having a default values. By default, we assume the number of legs is 4, the material is metal, and so on. Here is a stool, and the stool is a kind of chair, which means that it inherits all the values and all the slots that are there in the chair directly, except for those that happen to be different from the one in the chair. So as an example here, it overrides the notion that the chair necessarily has to have a back. In the case of a stool, the stool does not have a back. Axiomatic concepts were defined by necessary and sufficient conditions. Prototypical concepts are typical conditions. What about exemplar concepts? Exemplar concepts don't even have typical conditions, let alone necessary and sufficient conditions. In case of exemplar concepts, I can give you examples. Perhaps I can do some implicit abstraction of some examples, but that's about as far as I can go. Consider the example of beauty for a second. Here are 4 examples of something beautiful. Here is a painting by Van Gogh, here is a beautiful sunset, a beautiful flower, a beautiful dance, and so on. While I can give you examples of the concept of beauty, it's very hard to come up with a typical condition of a beauty. Exemplar concepts are very hard to define, and for that reason, they're also very hard to communicate to each other or to teach an AI program. Exemplar concepts can be culture specific, sometimes even individual specific. To summarize then, concepts can be of many different kinds, from very formal concepts like axiomatic concepts to less formal concepts like exemplar concepts. Of course, we can have even less formal concepts than exemplar concepts. Philosophers often talk about concepts called qualia, Qualia. Qualia refer to the raw sensations that we may get from our sensors. An example of qualia is bitterness. I'm sure you have come across some bitter fruit sometime or the other, and you can even taste it inside your mouth right now if you wanted to. But it's very hard to communicate what a qualia is to anyone else, what your notion of bitterness is to anyone else. Let us do an exercise together. On the left again is a spectrum from very formal to less formal. On the right here are 6 concepts. Inspirational, reptile, foo. Foo here is the same concept that we came across when we were talking about incremental concept learning. This is the same foo here. Right triangle, holiday, saltiness. Can you rank these 6 concepts according to the notion of formality that we have studied so far? What answer did you come up with, David?
So at the top I put right triangle because we actually defined axiomatic concepts as things that can be defined mathematically with necessary and sufficient conditions, and right triangle seems like a very emblematic example of that. Reptile I also put close to the top because in the biological definition there are necessary and sufficient conditions for being a reptile. They may differ a little bit from the way you and I think of reptiles, so we might have more of a prototype concept of reptiles, but in biology there is a very formal definition of what a reptile is. With foo, we kind of built our understanding based on different examples, so we had kind of a prototype view of foo. And similarly with holiday, you can think of examples of holiday. You don't really have a definition that something has to meet to be a holiday, but you can think of holidays as sometimes being a day that you get the day off. It's sometimes a day that's a particular day of the week or a particular date of the month. So there are different things that are overridable about different holidays. Inspirational is something that's a little bit hard to define what makes something inspirational, but you and I can very easily come up with some examples of some things that are inspirational, such as watching someone win in the Olympics or listening to a moving rendition of the national anthem. Those are 2 different things that are very, very different, but have the same kind of underlying concept behind them. And then saltiness reflects what you were saying earlier, Ashok, about tastes that can be very difficult to describe to another person.
So part of the point of looking at this different kind of concepts is that depending on the different kind of concept we are dealing with right now, we may come up with a different knowledge representation and a different inference method. Let me explain. Supposing we're dealing with concepts like foo or holiday or inspirational, then the case-based reasoning method might be a very good method for dealing with things of that kind. We may have experience with specific holidays, but we cannot abstract them out into a concept with prototypical conditions. On the other hand, if we were dealing with concepts like a right triangle or a reptile for which we can define necessary and sufficient conditions, in that case, there are alternative methods available that might be more suitable than case-based reasoning. So instead of thinking in terms of one method that is going to work for all conditions and all concepts, we might want to think in terms of an array of methods where each method is more or less useful for different kind of conditions, for different kind of concepts. David, I'm sure you recall Mendeleev, who was a Russian chemist who came up with the basic notion of the chemical periodic table. I'm sure all the students in the class know about the chemical periodic table, which organizes all the elements according to certain properties like hydrogen, oxygen, calcium, and so on. Now, Mendeleev came up with this notion of a chemical periodic table. In some sense, what we are trying to do in this course is to build a similar kind of periodic table, except that this is a periodic table of the elements of mind. It's a periodic table of the basic fundamental elements that compose intelligence. Instead of talking about elements and valencies and atoms and so on, what we're going to be talking about are methods and representations. So it is as if we are discovering the fundamental knowledge representations and organizations and reasoning methods that go with it. Case-based reasoning was one reasoning method that went with certain kinds of concepts that are hard to abstract into conditions like typical conditions or necessary and logical conditions. Let us build on this metaphor of periodic table a little bit further. So earlier we came across another method of dealing with classification, which we call top-down or establish-refine. In that method, we had this classification and hierarchy. We'd start with the concept, we'll establish it, then refine it, and refine it further if needed. That particular control of processing is very well suited for one kind of organization of concepts. It's very well suited for one set of situations where we know something about a vertebrate and we're trying to establish whether it's a bird or a bluebird. In a different kind of classification task, a better control of processing is to go bottom up. Let's look at this a little bit more carefully. Here are a number of leaf nodes, and we know, the agent knows something about the value for each of these leaf nodes. And the task is to make a prediction at the root node. So in this particular case, imagine the task of the AI agent is to predict the future of the Dow Jones Industrial Average tomorrow. It'll be great to have an AI agent like that. If we had a good AI agent like that, you and I could both become very rich. Now, how could this AI agent make a prediction about the Dow Jones Industrial Average tomorrow? Well, one way in which it could do is it could look at the information it has about the GDP and the inflation and employment today. But how does it know about the value of GDP or the inflation and employment today? Well, it could look then at the values of the overtime hours, the consumer sentiment index, new orders index, and so on and so forth. Now the processing is largely bottom up. We know something about the values or the features that go into this concept, and they go into this concept, and they go into this concept. We can abstract them and find the value of the GDP. And similarly for this, and then abstract it further. So the control of processing in this particular case, we might call it identify and abstract, identify and abstract. Bottom-up control of processing rather than top-down in the previous case. We have just defined two other elements of our periodic table, of our growing periodic table of intelligence. And this latter element, in the bottom-up classification, the conditions of application are different.
So how would you apply the principles of classification to designing an agent that can solve Raven's progressive matrices? In answering this, there's a lot of questions to touch on. For example, will you develop the classification scheme yourself, or are you going to have your agent learn it as it encounters new problems? So what will that classification scheme look like? What percepts will the agent use to classify new problems into that classification scheme? Then once it's classified them, how will that classification actually help it solve the problem? What will it be able to do this way that it wouldn't have been able to do otherwise? So today we've talked about classification, which is one of the biggest problems in AI. We started by revisiting incremental concept learning and reminding ourselves how it allowed us to take examples and abstract away a concept. We then looked at the idea of equivalence classes and how we can group sets of percepts into equivalence classes to establish a particular instance of a concept. We then visited hierarchies of concepts, such as the animal kingdom, where animals can be broken up into vertebrae, birds, and penguins. We then discussed the idea of different types of concepts, like axiomatic or exemplar concepts, and how each of them have different definitions and different affordances. Finally, we discussed bottom-up search. So instead of establish and refine, we look at the lower level variables and abstract up from them. Next, we're going to move on to logic, which is a little bit unrelated to this. But if you're interested in classification, you can look ahead to all our different lessons on design, such as diagnosis and configuration. They're going to really heavily leverage our idea of classification.
One could say a lot about the connection between classification and cognition. This is because classification is ubiquitous in cognition. You're driving a car on the street, you see a friend driving his car, you take a look at the car, and you say a Porsche, classification. You run a computer program, the output is faulty, you look at the output, decide on the bug, you name the bug, classification. You go to a doctor with certain signs and symptoms, the doctor names a disease category, classification. The reason classification is so ubiquitous is because it allows us to select actions. Once the doctor knows what the disease category is, she can suggest a therapy. Once you know what the bug is, you can decide on a repair for that bug. If action selection indeed is a very productive characterization of intelligence, then we can see why classification is central to cognition.
All right, please write down what you learned in this lesson in this box for us to peruse later.
And thank you for doing it.